arc length of the curve y equals f of x. In this video, definite integrals are used to find the length of a curve, also called arc length. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. Consider a function f of x that is continuously differentiable on the interval from a to b. We seek to determine the length of a curve that represents a graph of f of x measuring from point A on the curve to point B on the curve. When we know the horizontal and vertical distance between 2 points, we can calculate the straight line distance using the distance formula. But using the distance formula would not be a good idea because the curve is widened between them. However, if the 2 points on the curve are fairly close to each other, this formula provides a reasonable approximation to the length of the section of the curve. We can do this by dividing the curve into a large number of small parts at equally spaced intervals along the x-axis. Each small part can be considered a line segment. Each of them is the hypotenuse of a right triangle with legs of length delta x and delta y. With a little help from algebra, we can rewrite the equation as follows. We now add up the lengths of all the line segments so that the total length is given by. This is a Riemann sum. This approximation appears to improve as n approaches infinite. As n, the number of the line segments, approaches infinite, delta x approaches 0. That is, the length of each interval, delta x, tends to 0. It follows from the definition of the derivative that, and therefore the sum converges to the definite integral. We summarize these findings in the following theorem. The length of an arc length L, described by the differentiable function f of x equals y, between x equals a and x equals b is given by the integral. Let's see how it works. Show that the circumference of the circle of radius r is 2 times pi times r. The circle centered at the origin with radius r has the equation. We solve this equation for y. The derivative of the function is given as follows. With a little help from algebra, we obtain the integral. To solve this integral, we use the substitution t equals x over r and dx equals dt times r. When x equals minus r, t equals minus 1. And when x equals r, t equals 1. We now perform the integration with respect to t. Let's solve another example. The function has derivative given as follows. To solve this integral, we use the substitution t equals 1 plus 9 over 4 times x. When x equals 1, t equals 13 over 4. And when x equals 2, t equals 11 over 2. We now perform the integration with respect to t. You should notice that the integrals we obtained in the examples are not easy to compute. This is to be expected in general, since the formula that defines the arc length involves a complicated integral that includes a sum under a square root. Often, this integral cannot be computed analytically using non-integration rules. So we use numerical integration to approximate arc length when the arc length integral cannot be evaluated explicitly. If you do not remember how to solve integrals by numerical integration, you should watch the video that appears in the upper right corner of the screen to remember how to use the trapezoidal rule and Simpson's rule. The function x squared has derivative 2 times x. We now use the arc length formula. To solve this integral, we use numerical integration. We divide the interval into 6 subintervals, and then we apply the trapezoidal rule. Let's solve another example. The derivative of the natural exponential function is the natural exponential function itself. We now use the arc length formula. To solve this integral, we divide the interval into 4 subintervals, and then we apply the Simpson's rule. Try solving the next example yourself and then check the answer.